After that introduction, everything else is going to be anticlimactic. I'm sorry. I should just go home and you can go start drinking. Okay?
It's relative.
Can you hear me in the back? Good. So, Interstellar is a product of a failed romance. Back in 1979, Carl Sagan, the astrophysicist, a close friend of mine, called me up and said, I want to set you up on a blind date with Linda Obst. She's just been transplanted from New York, where she was science editor and counterculture editor for the New York Times Magazine. And she's out here trying to make movies, and she'd like to have a blind date with you. And so we had our blind date, and well, the romance didn't really go anywhere, but we became close friends. And many, 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 many years later, Linda called me up, autumn 2005, and she said, would you like to brainstorm with me for a science fiction movie? And I thought for a few milliseconds, and I said, sure, let's do it. And so this is the result. So what we conceived was the treatment. A treatment is a description of a story, characters, and in our case, the underlying science, the science venue for a science fiction movie. In our treatment, the science venue is general relativity, which we embedded into the movie's very fabric from the very beginning. Now, it's very fitting that I give this talk here in Copenhagen today, because tomorrow is the centenary of Einstein's general relativity theory. And so 100 years ago tomorrow, Einstein presented his theory to the Prussian Academy of Sciences in a lecture in Berlin. The reason I'm here today is I'm giving a lecture about the centenary of general relativity in Berlin tomorrow on the occasion of that centenary. And so we thought it'd be fun for me to come here and talk about Interstellar in the context of the centenary. So Linda brought on Jonathan Nolan. This is a very shortened version of this. If you go read my book, you'll get the longer version that involves Steven Spielberg, whom we worked with for a while, but who then dropped out. So I'm going to set Steven aside and talk about the people that really made this movie go in the end. So Linda and Steven, before Steven dropped out, brought Jonathan, or Joni, he's known to his friend Nolan, to write the screenplay. And Jonah had only written 3 screenplays previously. He was a newbie in Hollywood, and they had all been for his brother, Christopher Nolan. And so he was very committed, as was everybody else who worked on this film, very committed to making this be scientifically accurate and to understanding the science himself. So I fed him something like 30 or 40 books about science relevant to this movie, about geophysics, about planetary sciences, about astrobiology, about relativity and cosmology. And he read these books, devoured them, and then he brainstormed with me every few weeks about the science in the movie while he was writing the screenplays. So he went through 3 drafts of the screenplay between 2008 and 2010, at which point Steven Spielberg dropped out, and we sat for 2.5 years with no director for a movie that was going to cost between $150 and $200 million. They don't let just anybody direct a movie with that kind of a budget. Jonah's brother, Christopher Nolan, told us early on that if Spielberg drops out, he's maybe interested in working on it. He finally came around and signed up to write the final draft of the screenplay and to direct it in December 2012, and brought with himself his wife, Emma Thomas, as the lead producer. All of his films through his entire career have been produced by his wife. She's an amazing woman with a brilliant and very effective in making things happen. And once they are together on a project, it just goes like an unstoppable train, and through to completion with great success in all cases. So I laid on Chris at one of our first meetings what I hoped would be guidelines that he would accept for this movie, that nothing in the movie would violate firmly established laws of physics or our firmly established knowledge of the universe, and that those speculations that occur about poorly understood physical laws in the universe will all come from real science, and not just from the mind of some screenwriter, i.e. him or his brother. Chris embraced these guidelines, quote, to the extent it does not get in the way of making a great movie. And the next thing he said to him, his very next sentence was, and Kip, if you don't like what I do with the science, you don't have to defend me in public. So he was coming from a point of view where he was afraid that I would serve as a science police, telling him what he could do and what he couldn't do. Fairly quickly, after about 2 meetings with him, it became clear that we had a great collaboration going, brainstorming together, and that we together would search for ways to make the science work, and ways to get the science to accommodate if somehow it got in the way of making a great movie. And I'll give you one example of this later on. Chris brainstormed with me through 3 more drafts of the screenplay, and by the time Chris and Jonah were finished, the final screenplay and the movie preserved Linda's and my science vision, but Nolan's had changed the story and the characters essentially completely. So this is really their movie, and not Linda's and mine. This was not surprising to Linda, not surprising to me. I mean, these are great storytellers, but they built on the foundation we laid and aimed for a movie that would embody general relativity in its very fabric in a way that would be understandable to the general public and compelling for the general public. Chris, around the time he finished the 3rd draft of the screenplay, introduced me to Paul Franklin, who was the supervisor of visual effects for Interstellar. He had already received the Academy Award for Inception, and he would get it later on when Interstellar came out this past spring for Interstellar as well. So we won the Academy Award and the British analog of that, the BAFTA, for the visual effects in Interstellar. And most importantly, the visualizations of black holes and wormholes and other astrophysical objects that appear in the film, and which I was involved in with with Paul Franklin. So now I've talked a little bit about working with them. I'm going to let them talk to you about working with me.
We're still pioneers. We've barely begun. Our greatest accomplishments cannot be behind us, because our destiny lies above us.
The initial impetus for the project had been to say, why not examine real possibilities? Why not actually look at the real science there?
Luckily, we had Kip, and Kip is the foremost authority on all things gravitational.
The warping of space inside here scatters some of it back, light scattering off of the surface of a rippled ocean. Neither wormholes nor black holes have been depicted in any Hollywood movie in the way that they actually would appear. This is the first time that the depiction began with Einstein's general relativity equations.
The visual effects department under Paul Franklin and everybody at Double Negative took Kip's mathematical data and they created real visual representations of what a black hole is meant to look like.
The collaboration has produced visualization of things which nobody had ever managed to do before. We potentially may have discovered a couple of new things that were lurking there inside the mathematics, inside the physics.
So I cut it off there. You have now seen the major players that I worked with and talk about their enthusiasm for getting the science right. That enthusiasm went all the way from the top studio executives to the valet parking attendants. They had never experienced the bizarreness of working with a theoretical physicist before, and they all thought it was great fun. Now, the venue for Interstellar is the bulk and the brain in physicist language, or the fifth dimension, and let me is in the language of the movie, and let me explain what I mean by that. We're all accustomed to three spatial dimensions in our universe: east, west, north, south, and up, down. Time is a fourth dimension, and then in this movie, and in some very educated speculations about what really is going on in our universe, there is a fifth dimension that you and I have never experienced that leads out of our three dimensions into what is called the bulk. And I call that the out-back dimension. And in order to depict it, I have to remove one of our three dimensions. So I'm only showing you east, west, north, south. I've removed up, down. And now you see, so our universe looks like a sheet, a brain, a membrane. A brain is a physicist's name for short in place of membrane. Our universe is a membrane or a brain that lives in this higher dimensional bulk, this five-dimensional bulk. In string theory, there are higher dimensions, and there is reason to suspect that one of these higher dimensions in string theory is a big macroscopic-sized dimension, which might even be big enough for human being activity in a science fiction movie. And that's what we presume in this film. I'm going to, on my slides, whenever I have a slide, it has some science in it. I'm going to tell you, without verbally telling you about it, up in the right-hand corner, whether this is truth, we're really quite sure that the underlying science is the way I'm describing, or it is speculation, we're not sure, this is an educated guess. And it might be right, it might be wrong. So the bulk in the brain, the fifth dimension, is speculation. Now, the wormhole plays a major role in the movie. This is not the wormhole you see in the movie. This is the one that I played with as a child, the apples from the apple tree behind my home, growing up in Utah in the United States. Just imagine you're an ant, you live on the surface of this apple, that's your whole universe. It has two dimensions, but there's a third dimension that is your bulk that leads through the interior of the apple. And you have a choice in going from the top of the apple to the bottom of whether to go through the exterior universe or go through the wormhole, which is a shorter trip. So that's where the wormholes get their name. And this is a visualization then of the wormhole in Interstellar. You have Saturn here. The wormhole has one mouth that is near Saturn, an entrance. There's the core of a very distant galaxy, 10 billion light years away. And it has an entrance to the wormhole. And we have a choice of traveling through our universe on our brain 10 billion light years. So even traveling at the speed of light will take 10 billion years, as measured by anybody in the universe except you. If you move fast enough, it takes a lot less. Because of the warping of time for high-speed persons, observers. Or you can go along the surface of this wormhole to get in just a short distance, say a few kilometers, up to that very distant galaxy. And so this is the wormhole as seen from the bulk. In the movie, there is a set of characters who are normally called they in the movie, a very reverential they. At one point in the movie, very near the end of the movie, Cooper refers to them as the bulk beings. And this is characteristic of Christopher Nolan's films. Secret little bits of information will be somewhere in the movie, typically not at the place in the movie where you most want that piece of information. And you have to go back and see the movie 5 times or so in order to catch all these little bits of information. That's why this movie, perhaps that's why this movie sold 100 million tickets. This is the shape that Christopher Nolan chose for the wormhole in Interstellar. It's 2 kilometers across, and it is flares out, and this is the upper part of the universe in that diagram where the distant galaxy is. Saturn is down here near this mouth. Now, this is not the way you and I see the wormhole. This is the way a bulk being who lives in the bulk would see the wormhole. in order to figure out what you and I would see. Eugenie von Tunzelmann, who is the leader of the artistic team working with Paul Franklin, she and her team made paintings of the stars, the gas clouds, the nebulae, the dust clouds of this distant galaxy, this alien galaxy, which she put up here at the end of that mouth of the wormhole. And then down here at this mouth, we had the familiar Saturn and the stars on the sky in the vicinity of Saturn. Then I constructed the equations that were required to propagate beams of light from those stars and nebulae and dust clouds through the wormhole to an IMAX camera. And I gave them to Oliver James, who is the chief scientist at Double Negative, Paul Franklin's company that has 1,000 employees in London and 200 employees in Singapore. It's a company that has done computer graphics, visual effects for the Harry Potter movies, for all of Christopher Nolan's movies. Superb team. So he's the chief scientist, and he programmed my equations to produce the images that the camera would see based on light that is coming from that distant galaxy. And here's what then you see looking in from the IMAX camera. It looks like a crystal ball, and you see the distant galaxy distorted in the interior of the crystal ball, sort of like looking at one of these crystal balls that has a little Santa Claus and some snowflakes inside. But instead you're seeing a distorted image of that entire distant galaxy. Now, I'm now going to show you a trip through this wormhole, this very same wormhole that was used to make that image, as computed, again, using my equations and Eugenie's paintings, and as computed by Oliver James. The wormhole is here. It's much closer to you than Saturn, and so it looks big, nearly as big as Saturn. That's just because Saturn's much farther away. You see two images of Saturn, one image here distorted, another image very distorted there. This image is produced by light beams that come around the wormhole on this side, that image by light beams that come around the wormhole on that side. That explains what you're seeing. This is the wormhole itself with the image of the distant galaxy there, and we're beginning our trip through the wormhole. There's no music here because this is not the thing that appeared in the final movie, as I will explain. But we're getting close to the entrance to the wormhole. We're entering the wormhole, we're in the wormhole, we're out the other side, and the trip is over. Now, wasn't that exciting? So, a year ago last, I think February or March it was, they were in the process of editing the film clips that they had filmed and bringing in the computer graphics. And Christopher Nolan telephoned me and said, Kip, we got a problem. Could you come over to my house? And so I went over to his house, and he showed me, it wasn't precisely this clip, it was a clip much like this clip. And then he showed, and he said, it wasn't that exciting. And then he showed me the trip through the wormhole for other shapes of the wormhole, and well, they were better, but not a lot better. And he said, so what are we going to do? And I said, okay, you use artistic license. And this was the place where there was the greatest departure from the real science anywhere in the movie. And it was from the moment that the spacecraft starts to go into the wormhole onward, it is a trip through the wormhole that is made by combining images from different shapes of wormholes together with some artistic license and some weird music. So I'm going to show you that. I'm going to show you that trip, but I want to emphasize that up until the moment when Cooper, played by Matthew McConaughey, pushes the joystick forward to enter the wormhole, up until that moment, this is the real thing. This is precisely the way it comes out of solving the equation, Einstein's relativity equations, for the light that comes to the camera. So here we go. So this is the spacecraft, the Endurance. That's the wormhole. The Endurance is traveling along just above the mouth of the wormhole. Skimming along above the mouth of the wormhole. You see the galaxy on the other side. Still the real thing.
Everybody ready to say goodbye to our solar system?
Well, that was a little more suitable for an audience of 100 million people. But the fact that everywhere else the science was far more accurate than this is the only place where there was a major departure from the real science, I think says a lot about the commitment that Chris and everybody else working on the film made to the science. Do wormholes really exist in our universe? Unfortunately, probably not, but we're not sure. If you have a wormhole, whatever its shape may be, if it is empty, if there's nothing inside it, its walls will tend to pinch off. There's a gravitational attraction across the walls through the bulk. The interior of the wormhole is the bulk, and gravity crosses the fifth dimension through the interior of the wormhole. The walls pull on each other, and it collapses before you can get through the wormhole. So the only way that you can have a wormhole sustained is if you thread the wormhole with something that repels gravitationally. And that means something that has negative energy, negative mass and energy are equivalent according to Einstein. And it is possible to have that kind of stuff, that kind of exotic material, but it's made in very tiny amounts in the laboratory and usually only for a very brief moment of time. And when I and other physicists have tried to see whether the laws of physics would allow you to hold a wormhole open with that kind of stuff, the equations keep telling us probably not, but they don't give a definitive answer. And the fact that for 25 years, physicists have struggled to prove that the walls will always collapse and have failed gives me some hope that maybe wormholes can exist, can be held open. But I remain dubious, unfortunately. On the other hand, interstellar travel is unbelievably hard by conventional means. And so in Interstellar, we use a wormhole. And, but the humans don't create it. The wormhole is provided by the bulk beings. And the bulk beings are behind the movie in a number of spots like that. Black holes, by contrast, do exist. Black holes are truth, and we've got a big T up there. And I'm going to tell you lots of true things about black holes, some of them pretty bizarre. So as seen from the bulk, a black hole looks like a failed wormhole. It goes down to a point that it will turn out, as I will describe, as something rather more than a point, but something called a singularity at the center, which I will return to. But as seen by an IMAX camera, or any camera, looking at the black hole by looking at its shadow against, for example, a star field. If you have a star here, light can come to the camera around that side or around this side, traveling along the shortest path that it can on either side around the black hole. And so, as a result, you get an image like this. This is one generated by a friend of mine, Alain Riazuelo, in Paris. Here's the black hole shadow, and here are the two images of that star. Now, in reality, there also are many other images. The light can go in and go around the black hole several times and come to the camera. You always have the shadow, but it's much richer than you see in this particular drawing or this particular computer-generated image. And one of the things that Paul Franklin referred to in that little film clip I gave you is that we have discovered using the computer program that Oliver James wrote based on my equations, we've just discovered a huge amount about the so-called gravitational lensing produced by a spinning black hole when you have starlight coming from distant stars. But that's separate from the movie. I'm not going to talk about it any further. What I want to do is talk about the image of the black hole that you see in the movie and that has become sort of the iconic image for black holes in the modern era ever since the movie came out. Now, this is a weird-looking black hole, really quite strange. There's a lot of glare here. The glare can be explained in this way, that Christopher Nolan insists that everything is realistic, that you're not looking at the black hole with your eyes, you're looking through an IMAX camera, and the light from this, it's really hot gas around the black hole, the light from the hot gas passing through that IMAX camera is so bright that there is some scattering of the light in the optics, in the lenses of the IMAX camera, and that produces this glare. It's called lens flare. And in all the images in the movie that are computed by computer graphics by the double negative team, you have a lens flare. You see weird diffraction in strange, unexpected places in the movie, such as little colored chains of light that you wonder what that is. It's lens flare in an IMAX camera. Anybody who's worked with an IMAX camera knows that's lens flare. Anyway, so this is Gargantua, and why does it look that way? It's actually rather simple. Gargantua has a disk of hot gas, called an accretion disk around it, very much like Saturn's rings. And when light from the top back face of the accretion disk goes to the IMAX camera, it's bent by that warped space along this path. And so the camera thinks that the top back face is up here, and so that gives rise to this piece of the image. And the bottom back face, the light rays go down under the black hole and up to the camera, and so the camera thinks the bottom back face is down here. That produces that part of the image. Then light rays from the front of the disk go directly to the camera and produce the central crossbar part of the image. So it's all really very simple and really quite beautiful. That's what a black hole with an accretion disk would look like. Another piece of relativity that's very important in this movie is Einstein's law of time warps. And Einstein's law of time warp says that things like to live where they age the most slowly. And wouldn't you like to do that? And it says that gravity pulls them there. And it gives a formula that says that the strength of the gravity is proportional to the slowing of time. So in the case of the Earth, this means that the Earth's mass warps time, and the time warp produces gravity. And we know how strong gravity is on the surface of the Earth, and so we can compute with Einstein's formula for his law of time warps how much slowing of time there must be on the surface of the Earth compared to at high altitude. And it turns out, when you do the calculation, that it is a slowing of time by 1 second in 100 years. Now, that's not much of a time warp, but that's precisely the amount of time warp that's required to produce the gravity that holds us to the surface of the Earth. That means that in some sense, the Earth's gravity is very weak. By contrast with a black hole, such as a Gargantua, where the gravity is enormously stronger, and the slowing of time then is enormously greater. Now, in my brainstorming with Christopher Nolan, early on, he told me he wanted to have Miller's planet, which is orbiting around Gargantua, be so close to Gargantua that 1 hour on Miller's planet is 7 years on Earth. And I said to Chris, I don't think that's possible. And Chris said, Kip, go do a real calculation and come back and tell me what it says. Because I had been wrong before when I made pronouncements about what was possible and what wasn't, because we had brainstormed together and we had almost always found some way to make his ideas work. So I went home and I rechecked it, and sure enough, if the black hole does not spin, then the closest Miller's planet can be is here. Oh, I guess I need to explain what I'm showing you. This is the shape of the warped space around the black hole as seen by a bulk being looking in from the bulk. And so it's similar to the shape that I showed you for the wormhole. And the color coding is the slowing of time. So when you go from the green through the yellow to the red, time is flowing at 10% the rate it does up at very far from the black hole, say back on Earth. So this is 10%, a factor of 10 slowing of time. Down here where it's black, time is slowed to a halt, and so gravity is infinitely strong. And that's why nothing can get out of a black hole at that point. Gravity is infinitely strong, and so we call this the event horizon, or just the horizon of the black hole, below which you can't see. No signals can come out. But the closest Miller's planet can be, if the black hole doesn't spin, is at this location, where it turns out that 1 hour on Miller's planet is 90 minutes back on Earth, and that's nowhere near what Christopher Nolan wanted. And I knew this. I didn't know the precise number, but I knew it was something like 90 minutes. And that's what I based this on, but I also knew that the answer would be a little different if the black hole was spinning. And so I did the calculation for a black hole that spins. For a black hole that spins, there's a big change in that it creates a whirling motion of space around the black hole. The angular velocity with which space moves, like the air in a tornado, is lower at large distances from the horizon, higher close to the horizon. These white arrows are proportional in their length to the angular velocity of whirling of space around the black hole. And the remarkable thing that I discovered, much to my surprise, is that if the black hole spins fast enough, then the whirl of space stabilizes the orbit, so you can put Miller's planet very close to the horizon, and 1 hour in 7 years is possible. And so it wasn't the first time, it wasn't the last time that Chris was right and I was wrong in something. He said, go do your homework and come back. I will give you one example later where he was wrong, and anyway, we'll get there. Okay. So this slowing of time plays a huge role in the movie, a very emotional role, to the point that every one of the 100 million people who've seen the movie really understands, in a deep sense, the consequences of the slowing of time. Cooper, played by Matthew McConaughey, talks to his 10-year-old daughter before he goes through the wormhole and says, I may go near a black hole and time for me will slow down so that when I return, you might have aged until you're as old as I am. You'd be the same age. This actually happens. He goes down, lands on Miller's planet, and is there for about 3 hours, comes back out, and by then, Murphy, his daughter, Murph, has grown to be a brilliant 31-year-old theoretical astrophysicist, or theoretical physicist. And she's trying to, quote, solve the problem of gravity that I'll comment about it in a few minutes. And he goes down near the black hole once more near the end of the movie and comes out and meets his daughter. His daughter is now in her 90s, and he has aged hardly at all. This is a very emotional scene, emotional part of the film, incorporating Einstein's law of time warps. Now, on Miller's planet, there are very interesting giant water waves. I'm going to show you the film clip of one of these water waves. We see 2 water waves that crash over the lander spacecraft called a Ranger that Cooper and his crew have landed on the planet on. 1 hour apart. And I'll explain the consequences of that 1 hour apart in a moment.
How long for the engines, Case?
A minute or two.
Well, we don't have it. Helmets on! Brandon, co-pilot, you're up. Case, load the cabin oxygen through the main thrusters. We're gonna spark it.
Roger that.
Locked! Depressurizing! Engines up!
So that 1 kilometer high water wave is caused by what is called the tidal gravity of the black hole. The face of the planet that's closest to the black hole experiences a stronger gravitational force on it than the face that's farther away. And the gravitational force at the center of the planet is counterbalanced by centrifugal forces. And so at this face, gravity is much bigger than centrifugal forces. Here it is much less than the centrifugal forces. And so the planet gets stretched, pulled down by the excess gravity here, up by the lessened gravity, which is no longer balancing the centrifugal forces. And for similar reasons, the planet is squeezed from the side. And it is precisely that phenomenon by which the moon and the sun produce the tides on the Earth's oceans. Now, in this case of Miller's planet, what is happening is that unlike the moon, which always keeps the same face toward the Earth, Miller's planet has only recently been captured into this particular orbit. And so it's actually rocking back and forth as the tidal forces try to force it to not only be deformed, but to keep the same face toward toward Gargantua, toward the horizon. That rocking period, all I need to know is that the deformation of the planet is strong, but it's not torn apart, and I can compute the rocking period, and it's 1 hour. And 1 hour, it's rocking back and forth, and all that's happened is that the water in the Miller's planet's oceans is sloshing as the planet rocks, creating these waves. This is the analog of what is called a tidal bore when high tide rises and you have a nearly flat river headed out to sea, you get a tidal bore running up in the form of a big wave running up, well, moderately big wave running up the river. So the oceans slosh, they produce these 1 kilometer high water waves. The key to it is tidal gravity, which is familiar to us from the tides on Earth. And from this phenomenon, we can also read off using Einstein's equations that the Gargantua's mass is about 100 million times the mass of the sun, and its circumference is about the same as the circumference of the Earth's orbit around the sun. So this is a great big black hole. Turns out it's the same size, actually, as the black hole at the center of the Andromeda galaxy, which is the nearest large galaxy to our own. So black holes of this size are not unusual, but black holes that spin fast enough to stabilize an orbit of a planet close enough to have this huge slowing of time, that is very, very unusual and perhaps never occurs, that high a spin, though it is possible in principle. The laws of physics allow it. So that's all that we demanded in this movie, is the laws of physics allow it. Now, in the original version of our prologue to the movie, and in Jonah's screenplay, there was a prologue in which a black hole has orbiting around it a neutron star. This is a star that weighs about the same as the sun, and that has a size of circumference that is something like 20 kilometers or so. And this neutron star is orbiting around a small black hole that weighs a few times what the sun weighs. And it's going around and around, producing what are called gravitational waves, ripples in the fabric of space and time, similar to the ripples on a pond if you were to stick your finger in the water and stir it around and around. In addition, gravitational waves are also produced by the spin of the neutron star. As it spins, there is a little mountain on the neutron star, and it's emitting these gravitational waves. So you have two kinds of gravitational waves, one from the neutron star and black hole orbiting each other, the other from the spin of the neutron star. These waves travel out, they travel through the wormhole past Earth. They're too weak for people on Earth to notice until the neutron star is torn apart by the tidal force of the black hole. And at that moment, there's a very strong burst of gravitational waves. And this is discovered by Professor Brand and his colleagues who are looking with something called LIGO, the Laser Interferometer Gravitational Wave Observatory, which is a big mouthful that I'll just comment on briefly. So they see those waves, and then they, having seen the burst of waves, they can see the waves from the neutron star in their data going back over a few years. And they can then triangulate with those waves over the past few years and see where the source of the waves is coming from. And lo and behold, it's coming from Saturn, because this wormhole is in orbit around Saturn. But that's impossible. You can't they can look at the shapes of the waves. They can see that it was a black hole that's going to tear apart this neutron star. These things are heavier than the sun is. No way there can be that kind of thing sitting out there around Saturn. So this has to be that the waves came through the wormhole. That prologue, which was near and dear to my heart for a reason I will explain, got thrown away by Christopher Nolan in one of his first acts as a director. He said, "There's too much science here already, and I want us to add some more science." And the gravitational waves are not very important elsewhere in the movie. They got to go, along with a bunch of other things. And so that was the death of the prologue. But in fact, this was upsetting to me. I agreed it had to go under the circumstances, but there is something called the Laser Interferometer Gravitational Wave Observatory, which I co-founded and which has been tremendously important in my career. And this is something where you hang mirrors from overhead supports. The gravitational waves come along and they push these mirrors apart with the waves' tidal forces and push those together. The next half cycle, they push these apart and push those together. And that motion of the mirrors is monitored by a technique called laser interferometry. The distance separation between these mirrors is 4 kilometers. The motion of the mirrors from the waves that we expect to see from, for example, black holes tearing neutron stars apart or black holes colliding is 1/1000th the diameter of a proton or an atomic nucleus. The proton or atomic nucleus is 100,000 times smaller than an atom. And so the superb experimental team that has built this instrument is able to monitor the motion of these mirrors pushed back and forth by gravitational waves to a precision of 1/1000th of 1/100,000th of the size of a single atom. And this is unbelievable technology. It's just amazing what they have managed to do. This is a collaboration of 900 scientists at 75 institutions in 15 nations, with major presence of the USA, UK, and Germany, and Australia are the biggest participants in this. This is a photograph from the air of one of these instruments in Hanford, Washington. There's an international network. At the present time, the advanced instruments are operating in Hanford, Washington, and Livingston, Louisiana. We have an instrument ready to go into India once the Indian government gives its approval. The Japanese are building an instrument under a mountain, and the French, Italians, and Dutch have built one near Pisa, Italy. And we have a test bed interferometer that is a German-British collaboration that is test bed for testing technology for LIGO in near Hanover, Germany. So this is a big international network that will all operate together looking for gravitational waves. But at the present time, these two instruments are operational. I should just explain why we need these. We need the entire network to be confident that anything we see is real, to extract the shapes of the waves, which carries the information about what was going on in the source, to determine the direction to the source by the time delay in the arrival of signals at the different sources, the different sites of the interferometers. The advanced instruments, which we have been working on for many, many, many years, began their first gravitational wave search 2 months ago. So this is a very exciting time. And we're operating with sensitivities good enough to see colliding black holes out to 1 billion light years, 1/10 of the way to the edge of the observable universe. Over the next 4 years, they will be improved until they can see to 4 billion light years, about 1/3 of the way to the edge of the observable universe. And we are likely, with these instruments, to see lots of colliding black holes, colliding neutron stars, black holes tearing neutron stars apart, the engines of what are called gamma ray bursts and supernovae. And there are likely to be major surprises, that we will see things we never ever expected, because we're looking at a kind of radiation that is so different from light or X-rays or radio waves that it's night and day. And they will see such different kinds of objects from anything we've ever conceived before. This is going to give rise to a revolution in our understanding of the universe, and it is about to happen. So let me move back to the movie. In the movie, an important role is played by gravitational anomalies, and we see an example with dust that falls to the floor in Murph's bedroom when she's a child, and it accumulates in long strips that turns out to be a barcode carrying information. A tremendous surprise. Cooper tosses a coin, and every time he tosses it, it lands on one of the strips. Here we see one toss. It lands on a strip, not in between. It never lands in between. And he turns to his daughter and he says, "It's gravity." Something very weird about gravity, an anomaly, something like you've never seen before, something that violates everything we think we know about gravity, that it's enhanced along the strips and reduced in between the strips. Something is modifying the strength of gravity, and he just cannot understand what it is. But when Murph grows up and is a theoretical physicist working with Professor Brand, they struggle to understand what is modifying gravity. They want to understand these anomalies. In order to save humanity from a dying Earth, as those of you who have seen the movie are aware, by turning off the Earth's gravity temporarily so that giant space colonies can be lifted off Earth to get the roughly 1 million people who still have survived this dying Earth up into space to move to a new home around some other star. Their problem is they don't have enough rocket power to lift these space colonies. And so the fact that gravity is behaving so weirdly, it is enhanced or cut down in different locations, tells Professor Brand and Murph that perhaps there is some way to control gravity and to really turn gravity off. There are 16 blackboards covered with equations written by Professor Brand and by Murph, ghost-written by me, that explain what they think is going on. And it all has to do with the fifth dimension. So this is the fifth dimension up there, and these are brains, our brain and accompanying brains, and a lot of mathematics to work out how forces or fields that live in the fifth dimension are reaching into our brain and modifying the strength of gravity. And if they can really understand this, get the whole story down properly, then maybe they can learn how to control gravity themselves. Half of the answer, Murph realizes, is in their equations, but she's missing a very big second half, and the only place that she knows to find it is inside the black hole Gargantua, for a reason I will explain. So Cooper then plunges into Gargantua trying to get the information that Murph needs and Professor Brand needs in order to get the other half of the information in order to figure out how to control the gravitational anomalies. And here is this film clip of him plunging in.
Okay. I'm nosing down.
He's nosing down. You'll hear when he crosses the horizon.
Approaching the event horizon. Port side, dipping down beneath it.
He's inside the event horizon. And above him, looking back, he's now inside the black hole. Looking back, you see the accretion disk. you see the external universe now inside the accretion disk, and out there is the black hole subtending more than half of the sky. And the external universe has been squeezed down into this region. I'll let you figure out why it's like this. This is what comes out of the computer simulations. But I think you should be able to figure it out if you think about it for a little bit. Originally, the black hole was small and the external universe was here. Now the black hole is big and the external universe is in that little piece up there above him. Inside Gargantua, as seen by bulk beings, there is this singularity that I referred to before. It's actually a chaotic singularity and exceedingly lethal. Anything that falls into there gets torn apart and destroyed. Not just your body, but the very atoms of which your body is made. This chaotic singularity is governed by the laws of quantum gravity, and so that's why Cooper would like to go down there, and he could maybe observe the singularity and figure out from the observations, or send the observational data back to Murph, and she could figure out what the laws of quantum gravity are in 5 dimensions, so that she can learn how to control gravity. There's a problem, though, that although the other half of the information that she needs is there, the price for Cooper is death. That singularity, for him to get there and get the information, he would die inevitably. Fortunately, in recent years, theoretical physicists have discovered 2 other singularities inside a black hole. And they are much more gentle. This singularity, an infalling singularity, is produced by all the material that will fall into the black hole in the future lifetime of the universe. As seen by Cooper in his ship down here, because time is so enormously slowed down inside here, it all comes crashing down on him in a fraction of a second in the form of a singularity. Now that's pretty vicious still, but this outflying singularity, everything that fell into the black hole over the past life of the black hole, maybe 1 million years, tiny, tiny piece of it has been backscattered back up toward him, and it all comes up at him, sandwiched into a thin layer whose thickness is a fraction of a second as it goes by him. And that is a gentle singularity that he might be able to survive. And we as theoretical physicists don't know whether it's survivable or not. It depends on details. But in the movie, it is survivable. This outflying singularity, I should say, this outflying singularity was discovered just a matter, I think, of months before Chris and I started working together on this movie by Donald Merolf at the University of California at Santa Barbara and Amos Ori at the Technion in Israel. So Cooper falls into the singularity in the Ranger spacecraft. The tidal forces tear the spacecraft apart. If you look closely, you can see it torn apart, just a momentary glimpse. He ejects from the spacecraft just before it's torn apart. And then TARS, who has also fallen in, a robot, TARS is quicker and smarter than Cooper is. TARS collects the quantum data. Cooper and TARS are scooped up by a vehicle provided by the bulk beings and called the Tesseract, and it carries them out of our brain into the 5th dimension. Before I explain that, and I'm coming now to the end of the talk, this is the climax of the movie that is so puzzling. Before I explain it, let me say 2 things. First of all, what is a tesseract? A tesseract is a cube in 4 dimensions, 4 space dimensions. So if you look at an ordinary cube and you go up to this face, because of perspective, as you look into this face, those side faces, top and bottom face, they look like this. They look like distorted squares around the central square, which is the back face. Similarly, a tesseract looks like a set of distorted cubes, 6 of them here shown here, around a central cube. And this is really a 4-dimensional cube that there's a tesseract whose faces are 3-dimensional cubes. Okay, so that was the first thing I wanted to explain. All completely clear, I'm sure. And the second thing I wanted to explain is that In one of my first meetings with Christopher Nolan, he told me that he wanted to return Cooper to Earth traveling faster than the speed of light. I said, He said, go home and do a real calculation. And I said, I've done it. He said, go home and do it again. And so we went back and forth for 2 weeks, and then he threw in the towel and said, okay, you've convinced me. What do we do? And I said, we will send Cooper floating on the surface of a four-dimensional sphere, I said, through the bulk to come back to Earth. And Chris said, no, I'm going to float him in the face of a tesseract. And so it was Chris's idea to use a tesseract. The distance back to Earth in our brain is 10 billion light years. In the bulk, it is a very short distance, it turns out. And you can actually do the mathematics of the structure of the bulk in the brain using Einstein's equations and prove this. And so in a matter of a minute or two, Cooper can travel all the way back to Earth, floating in the face, in that face of the tesseract. The tesseract then docks alongside Murph's bedroom. So Murph's bedroom is inside this far face of the tesseract, three-dimensional face, and Cooper is floating in this face. Cooper can look up and see the top of Murph's head. He can look down and see the bottom of Murph's feet. He can look to the sides and see Murph from the sides. He sees Murph in every possible direction. So to Cooper, it looks like this. He's floating in the center, and there are all these Murphs around him, all doing the same thing. That's how he sees it. Chris then says, I'm going to modify the tesseract a little bit. I'm going to make Cooper's face be bigger and Murph's face be smaller. So you have these six bedrooms around him like this. And then I'm going to, he said, add on some more bedrooms, and I'm going to displace these bedrooms in time. And you can go read my book about the science of Interstellar to try to figure out what's going on here. But that's what he does, and there's several pages of discussion of this. And so you have here Cooper floating. Here are three instances of the bedroom, one above him, one on this side, one on that side. And here is a film clip of Cooper disoriented, just trying to get his bearings, having been carried by the tesseract up and it having just docked. So you see, she has a library, you see her books. You're going to see several Murphs down in here in different bedrooms, different instances of her bedroom. And then TARS has gotten the quantum data that are needed to save humanity, gives them to Cooper, who pushes on what's called an extrusion with his finger, which generates a gravitational force that travels through the interior of the tesseract to Murph, carrying information to Murph that has been collected, carrying the quantum data to Murph. It's going through the four-dimensional interior of the tesseract, and it pushes on the second hand of her watch in Morse code, feeding that information to her. The amazing thing is that when Cooper is doing this, he's been inside the black hole, he's been near the black hole twice, and Murph is actually 90 years old. However, Murph receives the information when she's 31 years old. And so the information, which has gone by gravity through the interior of the tesseract, has gone backward in time as measured by Murph, but always forward in time as measured inside the tesseract. And this is possible because there are what are called closed time-like curves in the interior of the tesseract. It's been built this way by the bulk beings. And the details are in my book. The very last figure in my book on the science of Interstellar. And so it has a happy ending, a Hollywood ending. Murph gets the data. She figures out how to turn off the Earth's gravity for a short while. Humanity's lifted up in space colonies and is aiming to move out through the wormhole to some habitable planet on the other side of the wormhole. So that, anyway, is the explanation of the ending of the movie. And I guess what I was going to say to you, and somehow I think I didn't say it to you, was that Chris, in one of our early meetings, said to me, "I've always admired Stanley Kubrick's movie 2001: A Space Odyssey, especially the ending, which is so mysterious. I want an ending for my movie, for Interstellar, that's going to be equally mysterious, but that can be explained. But that will be not understandable to anybody until they get the explanation." And so that's what he did. And I bet none of you had any idea what was going on, or much idea what was going on with the ending, until I told you or you read my book. And Chris gave me the pleasure of being the person who told the world what the ending is all about. So where to from here? My last slide. I'm doing one more movie, I think probably only one more, science fiction movie. Together with Linda Opes, me, and Stephen Hawking, we've gone through 9 drafts of a treatment for this movie, and it, I would guess, will be in the theaters in about 5 years. My last hurrah in Hollywood. Thank you.